Okay, so good evening, everyone. This is the third tutorial session on finite element modeling of welding processes. So we'll be continuing with what we had discussed in the previous session, as in we were attempting to solve uniform bar extension problem. We first started with derivation of the equations that it would be required for us to implement, and then today we will also be discussing about the coding aspects as to how do we actually write a code for solving the linear system of equations that we're able to obtain using the uh, through this weak form derivation of the governing equation. Okay, so let me go back to the problem. The problem is of a bar extension where E is as per the schematic that I have shared here. So E is the Young's modulus, A is the area of the cross section, P is the external load, and F of X is the distributed load. And okay, so the governing equation is given as the d of dx of E of x into A of x dux by dx plus F of x is equal to 0, where this part is the internal force and F of x happens to be the external distributed force. And the boundary conditions which are required for us to close the problem are u of x is equal to 0 is 0, and E of x, A of x into A of x, du by dx by dx is equal to P, which is the concentrated terminal load.
So here, what do you mean by internal force? Is internal force per length? Okay.
Yeah, internal force is the resistance, like what is shear stress, right? I mean, this stress. Stress is the.
But you're taking differential of it, and in on the right side is.
Yeah, it's something like that. Yeah, we should better call it. Actually, it is internal force is what we call as the stress, right?
Yes.
Yeah. So this is just
Cool. Sorry.
a way of writing stress.
I got it.
Yeah. And even this external distributed force is nothing but external distributed force per unit length, actually.
Yes. So this equation is from beam theory, right? If I'm not wrong.
Yeah, it's actually bar. Actually, since we are just studying.
Sorry.
Yeah,
I mean from that process.
yeah.
Okay.
And this is I'm okay. Now ask me why I'm calling it force. This is because if you look at the units, right? So this is Newton per meter square, and this is in meter square, right? So this cancels out to give us Newton, and du by dx is a non-dimensional number. This is the strain, actually, 1D strain. Yeah, and this is not per unit volume. Sorry, this is just per unit length. External distributed force per unit length. And these are the boundary conditions. Yeah.
Okay. So this bar is being subjected to both force per unit length and also point load, right?
So, okay. So we start with this form of the equation is known as the strong form.
Okay.
And what we do is what we first define the solution space. The solution space is the vector space in which one or more solutions lie. Essentially, it's just a collection of the functions which can, of which one or more functions will fulfill the requirements that it will satisfy the boundary conditions and also satisfy the equation. So if it's a well-posed problem, then we'll have a unique solution. and otherwise we may have multiplicity in solutions. So if it's an eigenvalue problem, then there will be a multiplicity of solutions. And if it the functions which belong to this vector space are that it must be C1 continuous. However, what we do is we give it stronger condition, which is what we call as L2. L2 functions. L2 functions means square integrable. So in L2 functions, square integral functions, the stringent requirement that the derivatives must also be continuous, that is no longer required. So it's like a slightly relaxed version of the relaxed version means, which means that we are considering more functions whose first derivatives may not be continuous. We'll actually discuss it about it as we go on. Yeah.
Yeah, I mean, I think in another way of explaining probably is the partial differential equation needs
Huh.
u to be twice differentiable. So we need all the
Yes.
functions which actually satisfies that condition. So
Actually, you will see it why we are taking the first order. The thing is because as per the partial differential equations, it should be second derivative. I mean, even the second derivative should also exist, isn't it? It should be
yeah, so
continuous.
oh, that's what. So the strong form requires u to be that one, but since you go for
Yes.
weak form, we have one easy thing. So we only have one
Yes.
time differentiable.
Right.
That's the idea.
Right.
Right? Yeah,
Yeah.
cool.
That's why yeah. So the requirement comes from the weak form. Yeah.
So here you also mentioned u has to satisfy at x equal to 0.
Yeah. So that is
There is one
required.
boundary conditions which is
So
explicitly on solution space. So, but in
yeah,
our boundary conditions, we also have that.
this boundary condition, right?
So we have two boundary conditions. Yeah. So does it sat? Oh, it satisfies both. Huh? Okay. Okay.
No, this is not required to be satisfied.
For the solution space. Okay.
Yeah,
Okay.
this is
Okay.
not required
Okay.
to be solution. Yeah.
Okay. Great. Great. Great.
So the thing is, as per the we only take those functions which satisfy the essential boundary conditions,
Okay.
not all the boundary conditions. Like these are natural boundary conditions, or what we call as the Dirichlet Neumann boundary conditions. This did not be satisfied by the solution function right now. It's only one of the solution will actually also satisfy this as well as this.
Yeah. Cool. Very clear. Very clear. Excellent.
Yeah. And since so once we have defined our solution space, now we also move to defining what we call as the variational or test space. So this is the vector space which contains weighting or test functions.
Okay.
So we are just laying down the abstract quantities. We'll use it here sometime later.
Yeah. Yeah.
So
Yeah.
here, from the needs, from the structure of our problem, right?
Yeah.
We'll see that the variational test space also has the same requirement that V should be an element of L2 functions. Is a more relaxed version, or C1 is a more stringent condition. And V of x is equal to 0 is 0, that's also a requirement. So it's like our variational space is the same as the solution space. But this need not always be true.
Yeah,
So
I heard there
if
is
say,
petrogalactic method. There are different kind of methods, and they won't match. So, depending on different solution species, there are different FEM
yeah,
techniques being
yeah, that's
considered.
one
Yeah.
thing. That's one thing. The other thing is, I mean, here what's the case is, say if you have here, right, at this part, see, like u of x is equal to 0 is 0. Say
Mm-hmm.
what if u of x, u at x is equal to 0 is u naught? This
Can you
part.
repeat? Can you repeat
If
what?
u of x is equal to u at x,
Oh, okay, okay, okay.
and the solutions space has to have that requirement that
Yes. While
however for
test
the
space could not be. Uh-huh.
yes, for the variational space, we do not require it to be. It will still be 0. The thing is because we are prescribing something already. So in that case, so like if u at x is equal to 0 is not equal to 0, then this implies that v is not equal to s. In that case, which means that at u at x is equal to 0, U is prescribed, right? So which means that we cannot take any variation at x is equal to 0. No variation at x is equal to 0 is allowed. So that's why v of x is equal to 0 has always to be 0, because we have already prescribed some quantity.
Yeah.
So we would not allow any variation at x is equal to 0 because it's prescribed. So even if say u of x is equal to 0 is equal to x naught, u naught, even then this has still to be 0.
Okay.
Okay,
Why
maybe I'll
is that?
just take a,
Why can't I
I will
have
just,
test space where my v test function at x equal to 0 is equal to e0? I mean, do you have any argument for that? I mean, why can't I have?
okay, so let's just, I'll just take a brief digression then, just to
Okay.
slightly introduce the concept of variations, right? Calculus of variations.
Okay.
Just this is a slight digression. So like a very, just call it a very brief glance at calculus of variations, right? So it looks like our attendance has stabilized now.
This is being recorded, so that's not. Anyways, yeah, funny.
Yeah, right. So I'll just, I think this will clear up all the doubts here.
Yeah.
So as per the calculus of variations, we start with some function. This one is equal to some, say x naught to xl, x1, and
Hmm.
function of x, y prime, dx. So this is called as a functional. Now you'll ask, why is it called a functional?
Yeah, because it is function of y. I mean, it takes functions and gives us a value, secular value. Yeah.
Yes, yeah, that's actually the answer. People always call it functional is a function of function. So that's not
Okay.
true, yeah.
Yeah,
So
it gives
functional,
scalar
yeah,
value also, no? It
yes,
gives scalar
exactly.
value. That's also important to mention. Yeah.
Yeah, so that is what, yeah, that's the best explanation of
Yeah.
function. So it's like anything which maps any value, any function, or any vector space to a real number.
Okay.
That is called as a functional in
Okay.
general. So even norm is a functional. Norm is not a function. It is a functional
Okay.
because
Yeah.
it maps a
Mhm.
function to a single value, to a real number. Even inner product is also a functional. It takes two arguments and maps it to a real number. Norm is also a function. It takes one argument and maps to a real number. Right? Now, say when we say this is our the form of some functional, right? You would like to minimize it.
Okay.
You know
So
that
what?
minimization is just an equivalent of
Di by dy
okay?
should be equal
Yeah.
to 0. That's a typical calculus we do, but I don't know how it should be done here. So do you do y plus h, that one? So how I of y plus h minus I of y h epsilon minus you do?
They say this subject to these conditions.
Okay. Okay.
Now, what you have to do is see what happens is you know that when we are trying to minimize of I mean of functions of this type, then we cannot actually plot it, isn't it? Because you don't know how will you try ordering two different functions. Ordering is possible only on only on real numbers, isn't it? So it means that you cannot plot. You cannot plot say y I versus I. That's not possible, isn't it?
True. 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 True.
Because the reason is because ordering is valid
Oh, that's nice.
only on real numbers.
That's very deep line actually. I mean, yeah, we know that why it is deep, but anyways, it's just a
Yeah,
few characters.
yeah, it's
Yes.
only valid on real numbers ordering that we can define what is known as less than or equal or
Yeah,
greater than,
completely
isn't it?
agree.
And if people say that, but how are we able to order alphabet? The thing is because those are like placeholders.
Yeah,
Those are A, B, C, D are placeholders. So A
yeah.
is just the placeholder
They
for
don't
first
have,
letter.
I think, value. Yeah, they're just placeholders. Yeah.
So they're like
They-
placeholders. So
yeah.
still means the same. We are actually instead of calling first letter, second letter, we are using letter A, letter B. So that's just a proxy for natural numbers, isn't it? So which means we cannot do this, isn't it? So which had it been say a single variable, then we would have actually plotted something and said, okay, these are minimum. Had it been had this argument been a single some real number, right? Then we could have just put
Yeah, yeah, yeah.
substituted. Yeah,
Yeah,
isn't it?
yeah, yeah. I agree. I
Yeah,
got it. I agree.
yeah.
I got it.
So which means that this is not our
Understood.
approach.
I'm
Yeah.
following. Yeah.
So just imagine that what we are doing is we have x, right? We have x and then y. So say some function, say this function, right? X naught to x1. Say this function is the minimum. Okay, just for the sake that this is a minimizer.
Yeah.
Fine. Assuming that we know the minimizer and it happens to be a convex function, so it will have one minimizer, one unique minimizer, right? So any arbitrary variations about this, isn't it? So let's call this y tilde. Just it's just like a function with some random perturbations to it. So it becomes just another function, right? This one.
Yeah.
It's just like we have added something to it, which is nothing but we have added this thing, say increasing, decreasing, and increasing. Say we have added this. This is added to y, isn't it?
Yeah.
To get y tilde, right? So which means that which means that the value of I when y tilde is substituted is greater than provided.
Greater or
Provided.
lesser? No, it can be anything. No.
No, the thing is, we are explicitly saying that we are minimizing this, right? And
Oh.
then we have already assumed that y
Yes.
is
Yes.
the
Yes.
minimizer. Y is the
I was
minimizer.
thinking in kind of inflation point, but anyways, yeah. Not inflation
Yeah,
point. Forget about it. Yeah.
yeah,
I was thinking
yeah.
another. Yeah.
So this is like we call it eta of x, right? So
Provided.
eta is, yeah, provided eta of x is not equal to 0 throughout, which means that simply I meant to say that eta of x is not a zero function, because if it's a zero function, then the equality will hold, right?
No. Wait. So throughout me, I think you should only write throughout except the boundary points, right? That's what you want to write there. I think.
No, the thing is at boundary point it's already the zero, right?
Sorry. Yeah, correct. I was just thinking.
Yeah,
Yeah, that's right. That's right.
yeah,
That's what I mean. Yeah, that's what I mean.
yeah, isn't it? So provided that this is not equal to zero throughout, which is nothing, it's nothing to but to say that if eta of x is not equal to zero, implying that this zero here stands for zero function, not the number zero.
Yeah. Yeah.
You know that there are zeros, right? In zeros depend on the context.
Correct.
So if you are looking at a vector space of
Yeah.
dimension n, then it's a collection of n zeros, isn't it? Okay.
So since here it happens to be a 1D problem, so we have zero function, zero scalar zero. So if you take a vector space, you think this net of x
Now
could
the thing
be
is, this is a zero function actually, which means that for all x, this will always be this is a straight line. Eta is a straight line. So this zero is a function which maps. So okay, ideally zero is a function which maps x to 0. So this is this 0. And this is the actual 0 that we use in our day-to-day language.
okay.
You understood? So it's
So
like
no
this is a
wait. So
function.
ultimately, what you're saying is neta of x is a function which is zero at x0 and x1, but not zero at boundary.
For other
You
points,
think,
yes.
no?
Yeah,
Exactly.
yes,
Okay,
yeah.
I got it. So in a similar context analogy, you have with text function space where it
Huh.
is zero at the boundaries, and
Yeah, so
did we get
you
to
will
conclusion, or we still have more to discuss about
yeah,
this?
now we have to, yeah, we are
Okay.
actually trying to approach that the thing that we plan to discuss here.
Okay.
So which means that we know that y at x is equal to 0 is y naught, isn't it? As I have written here, which means this is prescribed, and this is also prescribed. So that's why you see that when I'm adding perturbations, I cannot perturb at the boundaries.
Right.
The reason because it's we are not no longer solving the same problem. So that's where it
So
comes.
are
Yeah,
you saying that in FEM, whatever the
Mhm.
equation we have, we're trying to put it as a variation problem and trying to find
Exactly,
the minimum
exactly.
and just follows what the calculus variations is teaching us. Is that what we're
Not
trying to say?
always, not always. It
Not
depends
always.
on yeah. It's
Correct.
like the weighted approach. It happens to be a variational problem,
Okay.
but the conditions are that it is only possible to pose it as a functional if it happens to be some sort of a conservative system. Only if there is some
Mm,
conservation going on in the problem, right? Then only we can find the minimizer. Say if the system contains some damping effect, then there is no minimizer. The minimizer is always 0.
this is very interesting. But all the PDEs we consider, no, except
Hmm.
Navier-Stokes. Navier-Stokes may you have viscosity. It's kind of damping
Yeah.
only.
Huh.
Okay. But structures mostly it is damping free, right?
Not always. Yeah.
Not always. No, no, I agree. Even if you take two solids coming and hitting, you have
Hmm.
friction involved between them, and
Yes.
yeah,
Yeah.
it's
Yeah.
something. I mean, too broad to think of, but yeah. So there are so many basic problems where we can take conserved formulation
Hmm.
and get away to understand FEM. I think like you could understand basic FEM
Yeah.
using the simple
Yes.
like beam bending problems where energy is always conserved,
Huh.
right? But, yeah,
So which
that's a
means
really good
that
point.
if we don't have any energy dissipation going on the system, that problem can always be posed as a variational problem.
Oh, so what you're saying is calculus of variations mainly deals with it's not of FEM.
Yeah.
Calculus
Uh-huh.
variations mainly deals with problems where it is. I think you might also have formulations for problems where damping is also considered. Definitely,
Yeah,
of
but
course,
the thing is, in that
research is.
case, we cannot find the minimizer. Yeah, like it's not
Oh,
physically. It does not have any physical meaning.
oh,
Yeah.
maybe it is due to because if you take conserved system, no, the path could be anything, but you ultimately get it. But with when you take friction, it's not the same. No, the path
Yeah.
always is independent.
Yes.
No, the path is
Yes.
dependent on the friction, right? That's why
Huh.
you can't find the path. You have many paths, and oh, that's really
No,
interesting.
there is one more reason actually. The reason is
Okay.
because the minimizer will always lead to a trivial solution.
Okay.
That is actually the reason that our minimizer should not be 0 always, right? Then it's like a trivial solution. We are looking for non-trivial solutions.
Okay, that's one more reason. But yeah, I
That's
mean,
the, yeah. So yeah.
but yeah, I
So
see. So when you look
yeah.
at intermediate physics, basic physics, you say that kinetic energy, you have friction, then the path is no more same, you know.
Huh, huh,
So,
huh.
anyways, very interesting, very interesting. I can
Yeah.
clearly see the relation between them. I love them. Yeah.
Hmm, 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 hmm. Okay. Okay. So since this is done, so which means that we are only allowed to take variations at points where quantity is not prescribed. It's like we cannot take variations arbitrarily at any point. It's only where there is there are no conditions prescribed, then we can take the variations, isn't it? Non-trivial variations, yeah. So I think we'll go back to our, yeah. So in that case, if our even the boundary conditions happens to be a non-trivial one, like in this case, then in that this test space will still remain the same, but it will no longer be equal to the solution space. Right? We just took a detour to understand this concept of
Excellent.
variations.
Excellent. Yeah.
So I'll just mark it that there is a detour. Okay. Now we'll come back here. Now let's our goal is to derive the weak form of the governing equation.
Okay.
So what I did is I picked up the equation, and since what I have done is, since on the right what you see is this is equal to 0.
Krishna,
Yeah.
just interruption, small interruption, because this equation I was not there. I mean, I kind of know this equation, but I just want to tell you that. So you try taking an element, small element, and you're dealing with the forces acting on this element due to its neighboring boundaries, right?
Hmm.
That's
Hmm.
what you're doing, and you're just looking at the balance, force balance of the small element. That's what we
Yeah.
are.
So that is like the differential form.
Yeah,
So
it's
the reason, yeah, the reason is in strong form, the solution U has to satisfy at this equation, this condition has to be satisfied at every point. At every point, right? Like
yes,
derivative is
yes,
defined at a point, isn't it? So
that's
that's why
right.
it is not. That's why we call it as the strong form.
Okay.
But it has to be strongly satisfied at every point. But the thing is, that's very tough to determine. So that's why we move to a situation when we can find a weak form. Means we are looking at slightly reduced version, and we no longer want our solution to satisfy every point exactly. So say because it's a strong form, right? That's why we allowed it to have 0 on the right hand side. We can rearrange to have 0 on the right hand side. Now we'll see that as we come, right, as we progress forward, now we are going to what you call make some alterations here. So now what we do is we multiply both sides by v is an element of capital V, which
This function. Yeah.
is a test function here, and then integrate over the domain. So that's what we are doing. We are integrating over the domain. On the right hand side, what we are doing is this is 0 into v is will just give us 0.
Yes.
Isn't fine?
Yeah.
So now what we do is, so which means here there is some philosophical underlying in at this point. We are
Okay.
trying to say that we are no longer wanting this condition to be satisfied everywhere, isn't it? At every point in the domain. What we want to do is we want to we want to have a solution such that it just balances out the error
Hmm.
to make it 0 on an average sense. You see, right? It's like still we are averaging throughout the domain and then getting it to be 0. So this method is what you'll very much hear. This is called as weighted residual method. What we are doing is this was supposed to be residual. We'll just call it R. That it's it to be 0. This is just the philosophy. If this is understood, which means, yeah, I think the most fundamental aspect of FEM is understood. This is the only point where it just slightly becomes very much philosophical that why are we multiplying by a test vector, by a test function?
Yep.
So the reason is because we want to multiply with a function and average throughout such that it tends to balance out the error and make it zero. We are forcefully
No.
making the average error to be zero.
One question could be, why should we even multiply by the test function? Why can't we just simply take the integral and
Hmm.
and you know, I think it makes
Yeah.
sense, right? Yeah.
Uh,
Just a question. Just I know. I mean, this is a procedure
yeah.
developed by intelligence,
Yeah.
but do you,
Yeah.
can you give your insight in that?
Yes. So one reason is, say if we are having this, say if we are just multiplying r to be zero, right? Isn't it? If you are trying to do this,
Hmm.
then what will happen is let's just try to understand it why it happens, like why we don't do it. There has to be some reason, right?
Yes.
So say if this is zero, actually from here the only conclusion is that r has to be zero. But
True.
we are not
True.
simplifying our problem. Yeah.
True. Yeah, again, you solve the same thing, right?
Yeah,
Yeah.
that's yeah. It's like we are not doing anything to reduce the complexity of our problem because
No,
since
but
R can be generic, can be
that's right.
general.
That's right. So I'm just thinking, what are it's like maybe I mean, once we go ahead, I can see why V is helpful. What we are like, we are going into weak formulation. I can see that Yuka, the constrictions on Ru U could be reducing. I can see that.
Hmm.
I'm just thinking now here, like by multiplying with V, how like what advantage are we getting like just by looking at this equation I can't actually see. Maybe we should go forward, I guess. Only then I
Yeah,
can
yeah.
see, okay, only
Yes,
then I
yes,
can
yeah,
see, yeah, look
yeah.
now by
Right now
multiplying
the
v we are
advantage is, if you ask me, right, the advantage is what we are doing is we are taking R, which is nothing but this equation. This equation, yeah, this is R actually. This is because this is balanced to R, right? So this is our R. Now what we that it will balance out to give zero. Let's make some diagram. I think this then it will become very clear as to why we are doing this. Say as per our the term, right? We are driving weak form, isn't it? We are deriving weak form. So it's like if we had gone with our original assumption, I mean that r is equal to zero and r is nothing but where r is equal to EA du by dx plus f of x, right? So if we just integrated it over the domain, so the only conclusion what we know clearly from here is that r is already zero. So this is like trivially satisfied. You see, right? If we integrate this over the domain, it's already zero because r is
yes,
zero everywhere. It's trivially
yeah,
satisfied.
oh yeah.
So yeah, it makes no sense. I mean, like it does not help us.
We're solving the same equation but we don't know how to solve
Yes,
it, as a
yes,
numerical.
yes.
Yeah.
So what we are doing is we are multiplying it with a function v such that and integrating it over the domain, convincing ourselves that we are trying to have some sort of a I mean, this is some resultant function, say g, which will appear something like this. When you integrate it over x, this gives value to be 0. This is positive area and
Wait,
this
wait,
is
wait,
negative
wait,
area.
wait, 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 wait. This is very now because we have a graph. I mean, getting some good ideas here.
Yeah.
So, so R at all those points is 0, if you observe, right?
Yeah, but the thing is now we are no longer having
That's what I'm
non-zero R.
saying. So when you multiply
It's
with V, it is no more.
uh, yeah. So this is
But
actually some
wait, Krishna, no. Even with multiplied by V, it has to be maybe at a point. But when you take a section, maybe it is not. Can do you see the point? See, R is automatically 0 at every point, no? So you're just multiplying by a function.
yeah.
So
So which
RV
means
should also
yeah,
be 0, no?
no,
That's what I'm
yeah,
thinking.
yeah, yeah, yeah.
Please answer.
Just understand that this is no longer the same R
Ah,
because we are trying to have a function which does not actually satisfy this equation. It only satisfies it approximately.
no. I think no. No, I think RV is also 0, but when you expand it, maybe you see, if you go, can you go back once for the previous slide where you were showing all this stuff?
Hmm,
If you look at here, see, if
hmm,
you take integral 0 to L, he's
hmm.
multiplying dy dx, that full R, with v of x dx. Even here, so what you're saying is this d by dx of EA plus f of x multiplied by v of x is not 0. Are you saying that at every point at x? Can you say that? I mean, can we say that?
Okay, I got your point. You say
I'm saying R at each point is 0. So when you multiply it by v, it has to be 0. So at each point, that's what I'm understanding.
yeah,
Looking at the
yeah,
equation, I could be
understand. Yeah,
wrong.
understood. Understood. Yeah, yeah, right. Yeah, yeah.
Okay.
That's true. That's true.
So maybe when you
Mhm.
when you're looking at in discrete form, as in when you break it up, or should we look at it at all like that?
Yeah, and yeah, actually, I understood you. Yeah, you're right here. It means that R is still 0, but we are
Okay.
multiplying it with V
Mhm.
and just forcing it to be equal to 0,
Okay.
isn't it? Yeah, that's
Yeah.
true. That's true. Because there is a theorem which says that a strong form
Mhm.
is equivalent to weak form. We can
Hmm.
go the other. I mean, it's like if and only if it's like when we
Okay.
can proceed, go from strong to weak and weak to strong. So in that case, you are right. Like R is still 0. So I think I should not. This solution will be used later. This
Okay.
function, this function will be this graph will be used later. I'll just come
Okay.
to that.
Okay. Sure.
So
Sure.
let's keep it at here. We'll come back because this graph is will be used little later.
Sure. Sure. Sure.
So these are equivalent. So which means that R is still equal to 0, and this R bar will come to it now after some time. Isn't it? So like we put it here. This is known as weighted residual method. We have just weighted everything, and then we just want it average out to be 0. You see that we are just averaging out to be 0, and then what we do is we are just we for the first term we have separated out into different just broken down the integrals into multiple integrals, and then we integrated by part this thing here. This thing we integrate by part, and it leads to this expression here. See, right?
Okay.
Yeah, this here. So this is like doing integration by parts result in this. It gives us this, and then this is the term from the forcing function. So we can still go back from here to here. It's like either way. This is just like weak form, isn't it? And now what we did is this we have taken all this, and we can use the conditions that we have given for this. These are like boundary points, right? So we can use the boundary conditions. I think I'll just go back here. It looks like from integration by parts, this we get at the boundary terms, and this gives us a integral. And now what we see is you see something coming here, right? That there is one derivative operator from this here has been shifted to V. You see, right? This thing, this is a very crucial part here that you see during integration of parts, we shifted this differential operator to V.
Okay.
And this has reduced now.
Yeah. This is typical UV formula we are playing there.
Yeah.
Yes.
And then this is our boundary terms.
Yeah.
Now we come here and now we just use our boundary conditions for this term here. And that u at u is equal to v is equal to 0 at x is equal to 0 and ea du by dp is equal to p at x is equal to l. This we used here. Isn't it? So we use that. In the weak form we got as this. Now you can see something, right? Now you'll wonder why did we have C1 requirement on U?
Yeah.
No, it's clearly evident here that we only require U to be whose first derivative is continuous.
Yeah.
That's the only thing we require here. And in fact, using this equation, we can even solve problems with discontinuities, in which case we don't even require the first derivative to be continuous. All we require is the functions to be L square integrable, which means that U prime squared dx should be less than infinity. That's the condition we may
Yeah.
require.
Yeah.
And this goes into what we call as the Hilbert space, right? So
Yeah.
H1 space implies that it
Oh.
is L1 as well as, I mean, it is L2 for X, and it's also L2 for, sorry, L2 for U, and it's also L2 for U prime. This is what H1 implies, H1, Hilbert space. So the Hilbert space states that it must be, the function should also be square integrable, and its derivative should also be square integrable. Square integrable simply implies that the square integration should be less than infinity, which means that it must be bounded or it must be finite. So that's what the Hilbert space say. Ideally, Hilbert space, if you go, it only says that our inner product, isn't it? I mean, inner product should exist. So H1 is nothing but we just call as it's like Sobolev space of the Sobolev space we define as W, right? WP. So it's
Yeah.
nothing but W1. That's a more better word actually. But we just this has been traditionally called as Hilbert space. Ideally, actually, there is nothing but Hilbert. It's a Sobolev space of first order. So that's the thing here. Yeah. So that, and that's the reason we choose our first derivative and second derivative to be, I mean, the solutions and the variations to be
Yeah.
first order continuous. Now
So
what will
ultimately, I think we take any equation and multiply with. I mean, it's kind of that's not how I should speak it, but at least from, I mean, someone who doesn't want to get into too much mathematics, just take the equation, multiply by such function, integral, get whatever you get, and apply a FEM for that.
actually that is what FEM actually is used for. Like what you described, right?
Okay.
That is how we approach any problem in FEM.
Okay.
Because as we discussed some time back, that variational problem does not exist for
Mm-hmm.
we cannot cast every problem as a variational problem or as some sort of a minimization problem. However, multiplying by variations, it's always possible for any, even if it contains dissipation, we don't care. We can always multiply by variation and then carry out the same steps. However, we cannot come from first find a functional and then minimize it and then arrive at the weak form. That's not possible for all the type of what we like in shell theories and all that problems, right? There, people usually you'll find that they have actually obtained the energy function and then minimized it to get the equilibrium equations. But that is only possible for a purely elastic problem or
Yes.
problems for which minimizers exist, which means the energy is conserved. Yeah. or some sort of, it is a, mathematically speaking, it is a convex problem.
Oh, I don't know what is convex concave problems. Are you are mentioning it for, like this is the second time you mentioned that the
Yeah,
it is
yeah,
convex, but I don't know what. Okay, I mean, is
yeah.
it
Okay,
short?
I'll
You can
just
explain it if can you
yeah,
explain
it's
it
a
shortly?
it's like convex problem is say the way we describe is, so given this function f and x is the argument, right? So if the function, and then we take some point, this point, right? And we call this x1, let's call this x2. And then say we have this point here, this point, which can be described as x1, uh, let's yeah, x1 into yeah, 1 minus lambda. So it means that any point from,
I can't hear you. You are. I can't hear you. Something happened just
even
now.
now, not
Yeah, no,
not even
no.
now.
Maybe your
So
wire is maybe doing that. That's why sometimes I don't know. Check.
right, it's Bluetooth.
Oh no. That's what happened last time too. But anyways, let's continue. Yeah, suddenly it goes off, but now it happened. But it's good till
I
now.
see. Yeah.
Can you repeat
So
that? Mhm.
yeah, so it means that given a boundary, right, x1 and x2, these are the
Okay.
endpoints of the boundary, and then we have some function f here, and then we pick up any point lying between x1 and x2, any point.
Okay.
So which means that any point lying between x1 and x2 can just be found by linear combination from x1 and x2, right? Using this way.
Yes. Yes.
In this
Yes.
case, right? So lambda is equal to 0 will give us x1 in this expression, right? So like x is equal to 1 minus lambda into x1 plus lambda into x2. Say if lambda is equal to 0, then this expression will be x is equal to 1 minus 0, which is x1, and lambda into x2 is just 0, right?
Mm-hmm.
And if lambda is equal to 1, then we get x is equal to
X2.
1 minus 1.
X2. X2. Yeah. X2.
Right.
Yeah. You can write that. Yeah. Hmm.
Yeah. So which means that for every point in between, right? So the corresponding function value is how much? And let's just call it x tilde. I think that would be a fine. So it's like if f of x tilde, hmm, it's like we have considered this point.
Oh, that's
If of
interesting.
x,
How do you think the
if,
graph will be? It should be linear in lambda, no? So
yeah.
at
So this
x
is
equal to half, like at
this
zero
is the
point
one,
0.5.
right?
So at x equal to 0.5, what value it will be? I'm just thinking.
No, the thing is, we are just looking at just from a what you call functions perspective.
Okay.
So like I mean, if this point is x tilde here, then the corresponding function value will be this, right? This one.
Yeah.
And now what we do is let's connect both these lines, both the endpoints, and make it a straight line. Connect both these points, which means that this is f of x1 and this point is f of x2. So if we draw a straight line between f1 and x2, f of x1 and f of x2, now you will actually understand. Now we'll come at the definition of what is a convex function. Now, if f of x tilde, which is nothing but this is our f of x tilde, right? This point is of f of x tilde, isn't it? This point is of f. If f of x tilde is less or equal to lambda into, not lambda, we'll call it 1 minus lambda into f of x1 plus lambda of f of x2. If this is satisfied, then we'll call it as a convex function, which means that
This is kind of always less than. Is that what the
yes, yeah,
what you get? Less than or
less than
equal
or
to
equal
anything?
to, less than or
Yeah.
equal to, then it's convex. And if it's always less, then it's called a strictly convex function.
Okay. Hmm.
So if
So,
it was,
so you're kind of linearly interpolating between these how to function values, and you have
uh,
additional function which should always be less than those
yes,
two.
exactly. So in this function only you can find minimizer. You clearly
Oh,
see, right? Then only a
yeah.
minimizer does exist.
Yes,
And
yes, yes.
only if the equality, if this semi equality holds, right, then we can have multiple minimizers.
Okay. So I
However,
think, are you getting all this knowledge from any minimization courses you took? Because I can see that you have other dimension adding to the FEM here. Um, or is it just because you know FEM, you know all this stuff, or you because I know you took other courses as well. Is it coming in here,
yeah, it's coming
helping
also,
us
and
out?
rest are also from our what we do just here and there studies, right?
Yeah. Because I never, I mean, I don't know. I could be wrong. I never see convex function written in FEM. Do you find convex function? Do they even mention that?
Okay, what
Not in
happens,
advanced
Dinesh,
books. At
is
least some good. I mean, good
yeah.
books which are like
The,
engineering level
the
books.
thing is, yeah, the thing is, the convex functions. It's like any function which happens to be a convex function. Only in those functions you can
Minimization.
pose, yeah, as a variational problem, yeah, and then come back to the FEM. We can follow that we started the functional, and then minimizer will give us the weak form. That I mean, the weak that will give us the weak form after putting
Okay.
some minimizer, which we need to
Okay.
determine. So this is the, I mean, so it's like a convex function, right? Now we go back here, and now what I just kept it here till now, and now we just move to just taking like what we have done happens to be one parallel track. This is the
So
second parallel.
I have a okay kind of what didn't get you. What is parallel track?
Like what we have been doing happened to be one parallel track. Like
Okay.
this thing, the discretizing of the problem, and the building of weak form. These are like parallel tracks. They have to meet after some time.
Okay.
This go on, not parallel tracks, sorry. This go in parallel.
Okay.
This should be parallel. This is like domain discretization, and this was weak form. They will go in parallel, and then we'll actually merge both of them to obtain our FEM particle discretization. Then it comes.
Okay.
So it's like now let's discretize our domain. Okay, I have chosen say n segments,
Can
n
we just
segments.
want to ask? Just because of time constraints, so we will do next half an hour this discretization, FEM discretization. Then the half an hour we will discuss the example tutorial coding Phoenix.
Yeah. Actually, after this will be done. Let's
Right?
this
Okay.
discretization is very simple, right?
That's
You
fine.
see,
That's
it's
fine. That's
just
what I was
like
just saying. We'll really 1 hour left. Yeah.
yeah, sure. So we discretize the domain into Ln segments, and all of which the length is L by n. Then we can write our nodal positions as xi is equal to I of h, where I goes from 0 to n. So which means that for n segments, we have n plus 1 nodes, isn't it? Because n segments, and then there will be a node from left n and the rightmost nodes. Right? The next thing is to define what we call as the basis or shape functions. And here we use what we call as classically,
Okay. So we have
we tend to use,
basis functions, or I mean shape functions. You have test functions. You have solution functions. These three.
yes. The thing is, basis functions are nothing but test functions. We'll commit later.
Is it nothing but, or they're similar? That's what I'm trying to ask
No,
you. Because
if you use Galerkin method,
okay,
then basis functions are the test functions.
okay, okay. So what are we dealing with in our course? Like here, do we
Yeah,
deal
we'll
with
be using
Galecki
Galerkin
method?
because Galerkin method is what is used everywhere,
Like
and
typical
others
FEM.
like Petrov, Galerkin, and all that. Those are like research ideas. Still, we cannot implement on any general software.
Great,
So
great, great.
those are like
Because
research
you know, while
ideas.
we go to coding now, there I saw like some different things you were defining. So I want to ask, like, are
Yes.
these different thing or they two like similar also?
Yeah.
Can you
Right now we are
explain?
starting as if they are different.
Cool.
Yeah. Like shape functions in general will in only in Galerkin function the shape functions will be the same as test functions. If
Okay.
it is for other methods, we will still have to derive the shape functions, but they would not be the weighting functions. They would not be the weighting functions. We will be using some other functions as weighting functions. But I have never come across them because, yeah, that's like a topic of still topic of research in FEM. So like, so these basis functions are defined as shape functions. I mean, it's like hat in shape, right? Hat shape. So that's why we also in certain books will call it as hat functions. And it will have a value of 1 at the nodes, and at other points, at other nodes, the value will be 0. You see that? And this will for every node, for every basis function, that's how it is. And then what we do is we approximate our or describe our domain in terms of the basis functions. That's why you see that X is taken to be the linear combination of, or it's like the base.
I can't hear you. I can't hear you.
Not
Still.
even now. Huh?
Now it's good. Yeah. Now it's good.
Like we are using this basis functions and weighting it using our nodal cohesions, which are xi. This is what we call as the description of domain. Like this is how we just discretize the domain. And mind you that this still has a like it is still equal to the domain. Like we are just you are describing it using finite number of dots, but still we are able to construct the domain.
So, are you? This is strange. So x is equal to x of I and n of I, n of I of x. You have x and x. Like, do you see any
Yeah,
problem here?
yeah, this is the
This is
nodal
fine.
values.
That is
Nodal
fine.
values.
So on left you have x, and
And
on
these
n
are
of
the
I you also have x.
functions.
N of I is also function of x. You have like same
Yeah,
x equal to x.
yeah,
No.
this is like this is like something will go on, but we'll use it. We'll see it where it's used.
Okay, fine. I mean, it's not clear for me how.
Yeah,
Anyways, yeah.
yeah.
I don't see a
It's like
point.
which means that we can construct our domain. It's like a circular logic, but that's how it is. Which means that we
Fine.
can construct our domain using the basis functions and the nodal values, or say yeah, the nodal positions. Yeah. And we use the same basis functions even to approximate our u of x and v of x. See, right? It's u is still unknown, right? This we need to determine. U is our solution variable, which is the displacement that needs to be determined. But we are expressing in terms of ui and I. So it's like we need to compute. So it's like we only have to compute ui. Now you see, right? What's going on here is this u of x was a continuous function, but we will only find certain u's in the domain. So that is where you see uh, we move from an infinite dimensional problem to a finite dimensional problem. You see, right? So here, actually, this is not the actual u. This is not the exact solution we are looking at. Not exact solution.
Trying to find ui and you multiply by n of I because n of I is kind of interpolation between x1 and
Yeah,
x2.
we
So
already,
x1,
yes. Yeah, we already know. Yes, we
yeah,
already know
this
ni.
this yeah. I mean, I
Now
understand.
here,
Hopefully, the users which they see this video get it. So
yeah.
can we? Okay, I mean, I think I can also write no. I will try to give my just a little
Sure,
bit of
sure.
stuff if
Uh-huh.
we can write here.
Yeah. So here the thing is, last time I did not mention one thing, that this is not u actually. This is u of h. So u of h is something what we call as the Galerkin. This is like the solution function that we need to obtain now. is like solution function. I will discuss it at length later also because yeah,
Mm.
it's like too mathematical, so obviously it can't be understood in just one lecture.
Yeah. So you shared me somewhere. Sorry, I'm taking time.
No, it's okay. The thing is this I have not yet shared for editing.
You
Yeah.
shared. You shared. Are you editing in the same?
Yeah. Yes.
So it is the third one, right?
Uh-huh. Yeah.
Okay. Cool. Great. So I have is yeah. Can I hope I can editing. Oh my god, this is such a good thing. Sorry, I don't think I can edit the same
Yeah. See.
time.
Yeah.
But what I want to say is, in a way, can you draw a sine function in a new slide? Just want to tell you can understand. Yeah, just draw a sine for continuous sine function. Um, I mean, I know. Just want to make it more clear for users if they watch it. Uh, that
Yeah.
in one dimensional sine, of course, is one dimensional. So you can
So
draw
that
it like
will
simple sine function. So it is continuous. So at each point you have several values, right? Yeah, that's enough. That's enough. That's enough. Simple.
yeah.
So 0 to pi is good. Okay. So at each point you have like it has infinitesimal what? I don't know what to say. It has so many points. Function values so many
Exactly.
points.
Infinite.
But
Infinite
yeah,
points. Yeah.
so on computer you can't solve for each point. Okay, so
No.
ultimately in
No.
all our equations you want to solve for u, which is the displacement of the bar at each point, but we can't do it because infinitesimal computer don't have that much memory. So what we want to do is we want to find the values at certain intervals. So we discretize the sine function into several points. Like you can see, like you can
Hmm.
discretize maybe 4 points here or 10 points in between. You can cut them like, okay, and we are only trying to find the function value at those points,
Right.
and at every other point which we are not solving, we will just interpolate using those basis functions.
Hmm.
So that's what we are
Yeah.
trying to do. So maybe I'll try to add a slide once this is done, and we,
Sure.
we will we'll make the presentation
Yeah.
open.
Yeah.
Yeah,
Yeah.
yeah, cool. Let's continue.
So it's like that we are not actually finding the exact solution here. We are actually finding a solution function which is UH. I did not put it
Oh,
last time here.
yeah,
There
yeah,
is something, and UH happens to be approximately equal to U. It's not actually equal to U. So
yeah.
we are actually moving to a numerical framework, and that is known as the Galerkin approach.
Okay, okay.
I will actually come to. I will show I'll show you where we use it. But essentially, so what we have done is, uh, so it was like we were here, and then what I did is I actually express this integral right in terms of this integral here, this integral here. I just broke into it into multiple subintegrals from x0 to x1, like element-wise integration, x0 to x1, x1 to x2. It's just like ultimate integration is just a sum of smaller integrals, right? So it's 0 to L. We can just break it down into smaller segments and integrate it. You understand what I mean? It's like we have this. We had partitioned our this one, right? Our domain.
Got it, got it, got it. Clear, very clear, very clear.
Yeah. So we are doing that. Before that, I must have said that we are actually finding the Galerkin weak form. I must have said that time that we are actually looking for Galerkin weak form. So in that case, we are not actually finding for the actual U, we are finding for U of H and V of H. So wherever you have, so it's like H indicates the width.
Okay.
So it's like an indicator of the discretization. So if H tends to 0, means that we have approached the analytical solution, right? Isn't it? From here, you look at this.
I see, I see, I see. As h goes to 0, we have to get back to the original equation. I see that. I see that.
No longer the weak form that we started with. This is known as the Galerkin weak form or simply Galerkin form. Means that now we cannot, from here, we cannot retrieve our strong form anymore. That's gone. We have lost the strong form.
Acha, acha, okay, okay, okay,
So
okay.
now what we'll do is we will even our
So what are you trying to say? What are you trying to imply by saying that? Like we are no
yeah
more on strong form. We get VH to 0 2 still. So
yeah, yeah, last time I had mentioned that we can move from strong to weak and weak to
oh
strong.
yeah, yeah, not anymore.
So
Okay.
that's not
This
anymore. Yeah.
why do you
So
think
now
so?
it's
No, no, even
yeah
say
that's
that say that
yeah
can we
yeah
can't we rearrange interchange you can't do that anymore?
no because
No,
U of
because we
H is
applied
no
those
longer.
conditions, like we applied V as 0 at boundaries and all we remove. So we can't.
Yeah, so it's like U of H is no longer U. Now the thing is because we are choosing from a different set itself. So we are picking up from a set SH where say U of H is an element of, again, I'll just call it C1, but we can also use H1. Maybe I'll just call it H1. I think that is H1 of 0 to L, such that U of H is equal to 0. So this is like a subset of S. So which means that we had a set containing all the solutions, I mean, of which one or more could have been the solution to our problem. But now we are only looking at a smaller set now. This was S.
Yeah.
Now we are
Yeah.
only looking at this many solutions. So which means that what we see is that UFH is summation of UI Ni of X. This is what we choose, right? So it's
Mm-hmm.
like this is our basis for the basis
Mm.
for S of X. So you see right now it's a finite dimensional problem because we only have a finite number of basis functions which can span the entire vector space. However, for this was an infinite vector space, but now we are looking at finite vector space. So which means that if our solution were here, which we can never get the solution. If by chance our solution happens to be here, then we are actually able to retrieve the actual
It
solution
is
from.
like we're just saying that these, so whatever the solution I get, that's a really good point you're making here. So I think
Hmm,
our solution, this is a really good point I want to make here. Say you take the PDE and
hmm,
say that the order of the solution which the PDE solves could be second
hmm,
order or third order. Like you
hmm,
don't need more than that, no? Like any solution can be a combination of some basis functions.
hmm,
So
hmm,
in a similar way, here, um, so like infinite, like all these spaces you have so many order of functions, but we're only looking at this basic, like first order, second order. So that's why we say like hamara this discretized form is approximately second order, like second order approximation, third order approximation, first order
yeah,
approximation. That's what we say. So
yeah.
we took the
It's
exact.
like it's like analogous. Yeah, it's like
Excellent, yeah, we
analogous.
take the
The
exact
idea is
equation.
analogous. Yeah.
Take the exact equation, we say that so this exact equation needs you to be second order approximate to have the
Hmm, hmm.
exact solution, right? The exact
Right.
broad
Yeah.
problem. Then we made
Hmm.
it into weak form, and weak form only
Yes.
needs to have only first
First
order,
order.
and
Yes.
our
Exactly.
basis only needs first order functions. So
Yes.
that's how we see it.
Yeah.
So even you take
Yeah.
the real equation and you have 3 4 order basis, there's no point, and it's really beautiful.
And
Yeah.
now, and now we have made one more reduction that we have actually reduced the number of functions we are looking at.
Which means.
which means that before we are looking at that all of the members within this S can be a solution. Any
Correct, correct. That's what I'm saying. Yeah, exactly. No, yeah,
but
yeah,
now what we are doing is we have reduced some. We can also call it that we have reduced the area in a lake where we are fishing now.
correct.
Before we were what we call fishing in the entire lake. Now we have just chosen one segment. So if this segment happens to where the colony of or the population of fish lies, then we are able to catch it. Otherwise, we may not. So it's like if the solution lies in this, then we are able to get the actual solution. Otherwise, we are just happy that we got something which is closest to the solution here. Like we are just trying to minimize the distance between the actual solution and the approximate solution that we are trying to find using FEM. This is like we'll discuss it again. This is a very what you call somewhat like philosophical aspect in FEM here. We'll come back to it later. Like this will take us time to to familiarize, right? So
Yeah,
we'll
but
come
it's
to it.
pretty clear for me so far. I mean, it's really
Yes.
good. We're going really well.
Um,
Yeah.
so now what we do is now I just pose a question that okay, there are so many elemental integrations here going on. So can we not have an approach? So I was just posing a question that can we not have an approach where we do not have to carry out all these integrations? Like there can be, if you have 1,000 elements, we'll have 1,000 such integrals. Can we have some way where we do not compute all of these integrations? Can we just automate it? Or can we have some template? So now our goal is to find a template. So here what we
Okay.
do
So
is,
taking like one element and you making boundary conditions there and trying to solve for the
no, no, no,
single
no.
element.
No, it's like we are just taking one element and integrating it to determine this integral here.
Okay, fine, fine, fine.
Likewise, so it's if we have 1,000 elements, then we'll have 1,000 such integrals on the right hand side, on the left hand side as well. So it's like 2,000 integrals. But can we not have a template which will reduce this 1,000 integral just to know one integral, and using it we can construct all of them? So we are taking one model interval which goes from -1 to 1, and then mapping it to one segment of our domain. So you see that it maps to xi minus 1 to xi, that one interval or in the domain. So we are doing that. So this is like we are mapping from parent element to physical element. We are just mapping. And then we are constructing safe functions for that. And then it has to satisfy that relation, right? It has non-zero value at the node for which the safe function corresponds to, and zero at all other nodes. So in this case, we'll have two nodes. So it's like n1 will have one at here for the first node, and n2 will have one at the value of one at the second node, and at other nodes it will be zero. Because ultimately our interval is just a small line segment with two nodes, right? So we are mapping from here to here, and then we are also able to map this our interval as well using the basis functions here, and also the solutions in this. I think these are like very nitty gritties. We just not need to know once in any software. We don't need to do this. These are like some routine tasks which are done, which is carried out by the software. We don't have to, but we should just know what's going on here. So this I have done a little bit of algebra, and then we will see that we are actually mapping the integral from xi minus 1 to xi to xi is equal to -1 to xi is equal to 1 using some change of coordinates, and we are actually able to determine this. See, now we have a general approach. So any interval we can just map it to xi is equal to this particular bi-unit domain. And likewise for even the functions, for even the forcing function, we can also do the same. Now we have been able to create a template to find general integration. And this is when our E, F, and A are functions of X. because we clearly say that E is still a function of X. Area is also a function of X. However, if in order to find a very general template which is valid always, then we will need to slightly simplify. In that case, E, A, and F have to be constants. Then in that case, even the integral over this one segment will just result in a small in a repeated template. Like this is the template. So this integration evaluates to this expression here. That's it. This we can use for all the what you call sub integrals. Likewise for functions, the forcing functions also are able to do it. From here we get what we call as the elemental stiffness matrix and also the force matrix. And what we do is now we assemble the elemental stiffness matrix to form a global matrix. And once we do the global matrices, we are just adding up the contributions from all the elements to form a global system. Likewise for forcing functions. And then this is our expression here. So ultimately, this is the expression which we need to solve. This is the system of equations. See that? So yeah, this is where our previous session had ended.
Okay.
Now, as we mentioned in the previous, that in the next class we'll just solve the matrix equation and compare with the analytical solution in Python or MATLAB. But yeah,
Perfect. Perfect.
but we shall also generalize the approach for arbitrary E and F variation. We'll do this, I think, in by the next session. Okay, so what I'll do is I'll just share the code that we had written that for Phoenix. I'll just stop.
Probably we should. Okay, now you can explain it, the Phoenix thing. Next time, if I learn something and even I want to share, we can do the Phoenix thing in Google Colab, like the Jupyter Colab, where we both can edit it at the same point.
The thing is, can we install Phoenix in Google Colab?
We should be able to, but it's so big. I think it's big. It, it doesn't work
It
like
did
that.
because
We have to look into it. No, we can look that. We can look into it. Have you do you think it is important, or it will be nice if we can show how to install Phoenix X, because I don't know how much difficulty you might have had.
no, it's very straightforward. Very
It's straightforward
straightforward.
now, because last time we remember we were unable to make it work, and
Yeah, the thing is, it was the issue that issue is still not resolved. Yeah.
okay, that is it Phoenix X or is Phoenix?
No, the thing is that is issue with the graphics renderer package.
There is
So
graphics is always a problem, dude. Yeah, even PySPH has similar issues.
so
Professor
which means
Prabhu.
that it does not. It has issues with Windows subsystem on Linux. But
Okay.
it does work on pure Linux. There is no
Well,
problem.
Linux is always works. That's why it's
Yeah.
amazing. Yeah, good, good.
Yeah.
Okay, let's look at the Python thing and we can.
Yeah. So one way of, I mean, solving that issue is to use some other visualization package that we had seen, right? Some starting from T, or I just forgot it. Some other package it was.
So this Qt, people do Qt. There's so many versions of Qt, and you don't
Uh,
use Qt to something else. So I don't know, but usually people find this visualization package is really pain painful. I have found, but coming to the current tutorial, so I have found few comments. I will tell you. I mean, I can tell you while you was to start to share the code.
Sure, sure. I see. Okay, I think the screen is being shared, right? The
Not yet.
not yet.
Not yet.
Uh, Now?
Yeah, now I can see. I mean, it's not. Yeah, now I can see.
Yes, yeah. So it's like we are determining the axial deformation of a bar using Phoenix package. Yeah.
Yes,
So the
correct.
problem description eventually gives us the bilinear form A of u is equal to L of. Actually, I had planned to write it everything indirectly, but
It's
I don't know
okay.
whether it's worth the time. Just wondering.
We'll take our time. So if we are able to cover, like we want to make something Like I think FEM, I think we need 4 more lectures to cover it in detail, right? So if we
Yeah,
have
yeah,
more time now, we can add more content to this and make it self-sufficient. This idea,
yeah.
like
That's what. Yeah.
whatever wrote the notes you wrote, you can kind of make it
Hmm.
into equations, LaTeX, and kind of show this is how it is.
Exactly, we can do it here. You see, I'm using Markdown.
Yes, yes, yes. I know. Yeah, yeah, yeah.
Yeah,
Of
that's
course.
right. Yeah, I'm sure you're aware of this. It's just like,
Yeah,
yeah,
of course. I mean, I've been doing this from MTech, so
right, right. Yeah.
yeah, love it. Yeah. So it started out to be only Python's thing. So it was, I think, IPython notebooks. That's how it started.
Huh, huh,
Okay.
huh,
Now it is
huh,
Jupyter notebooks. Matlab, you
huh,
can do Julia, C plus. Now you can do anything in this. Julia, C plus plus, like any language now they are doing. So
hmm,
you can
hmm,
run C
hmm,
plus
hmm,
plus. You can do like a lot of things with these notebooks now. So
hmm,
yeah.
hmm.
Anyways, let's continue. Yeah.
Oh, yeah. So I have just, yeah, picked up this from some source.
Yeah. Some University of USA University. That's what I saw. I saw the source. Looks like
Hmm.
from somewhere in the US. Yeah.
Yeah, yeah, yes, yeah, yeah. So now we have this, we are loading the Dolphin packages, right? All the Phoenix packages, which is
Right. So,
Dolphin.
Mike, I had the comment I had was, why do you need MPI? Because some people may not install MPI on the systems. That's one thing. Okay. And
Yeah.
I saw in the comments. So you are using MPI to define the mesh. So to create the mesh. So like imagine it may not work now. So it's better not now. I think definitely this works. I'm sure because MPI is there in every system as far as I know. If you can
Uh-huh.
avoid this MPI usage, then it can work without like serially also. Just giving you my 2 cents knowledge. So, yeah.
No, okay, I'll tell you. So that is where Phoenix differed from Phoenix. Phoenix
Ah,
X differed from Phoenix.
okay.
Yeah, so it's like Phoenix was based on a very different paradigm. So it's like Phoenix is a completely new package. You can like it's very tough to. I mean, it's impossible to run any Phoenix tutorial cases using the Phoenix program. I mean, the library. So
Great.
they have completely overhauled it. So here, even if you're not using FMPI, we still have to import MPI files.
Okay.
So it's
Mhm.
like, and so I'm using imported Dolphin. So Dolphin is the most fundamental FEM engine for Phoenix library.
So something I want to investigate in the future tutorials is what is this Dolphin X exactly doing regarding to our FEM algorithm? Because in FEM algorithm we have to solve it, we have to arrange the matrices. So we have so many things, right? In our like I think
Uh-huh.
if we take more time, we can clearly bring out what are the main essential black boxes. So we can
Yeah.
kind of we can make one is discretization, one is mesh creation, basis functions, multiplying that this we can look at it at some point, but anyways, yeah,
Yeah.
something to
Actually, here
look at.
we'll be approaching it from the very way we actually described our problem right now.
Can you actually zoom in maybe like 3 times?
Okay.
Control plus plus, if I don't know you can
Okay.
do it or not here. Can you
Yeah,
zoom
I
in here?
can.
Yeah, this
Yeah,
is
I can.
perfect. This is perfect. Yeah,
Maybe I'll just close this.
it's perfect. Yeah, it's more
Yeah.
perfect.
So it's like I'm using all the loading all the Phoenix packages. So Dolphin X is the FEM engine for Phoenix library. What it does is it converts Python-like syntax to C++
Ah,
code.
okay, I see.
And then you have UFL, whose full form is Unified Form Language. It provides like a for mathematical expressions using. I mean, it's like we can convert anything. Like if we can use grad word, it will perform gradient operation at the backend. We'll just come to it, yeah, as we move forward, right? And this we know very well. It's numerical Python package, yeah. So I'm using this one, right?
Something, mathematical software for Python. Yeah.
Yeah, I'm using that what do you call GitHub Copilot. So it automatically
That's
completes
all
it.
right. That's all right. It's all clear.
Yeah,
MPI we know.
yeah,
We know PET-SC. PET-SC is to solve the
yeah.
linear equations.
Yeah, this is for
So PET-SC is a thing which is developed by I think this guy Grop, Michael Grop.
which one?
I
Which
was
one?
mentioning, Michael Grop. I think. Let me check. Yeah, Bill Grop. Bill Grop.
I see. Hmm.
but his name is William D. Gropp, but people call him Bill Gropp. So I think he developed this PET-SC. So he's right
I
now
see.
director of I think somewhere in the US big laboratory. He's director of high performance computing. Uh, yeah, so he developed it long back to solve the linear equations. But
Hmm. Hmm.
something we can explore at some point is we're only running this on CPU. Okay.
Hmm.
So if we have time, maybe once we establish basic FEM and we have time now, we want to look at packages, we can run this stuff in GPU as well. And we can see how to run stuff on GPU. Some numerical, some basic, like same, because this is ultimately we're solving linear equations,
Hmm.
right? So everything is okay. Once you have the linear equation, that's a thing which takes a lot of time to run. So you can
Right.
actually port them to GPU and run them and bring them back, so we can see
Hmm.
how we can do it. If see like which packages are there, it will make our computations faster and something to learn, which is very much applied to modern world. I would feel
Hmm.
personally. You understand, right?
Yeah, yeah, yeah. Right,
Cool,
right.
cool, cool. Yeah, great,
So these are just I had just added this time
great,
sys. Right
awesome.
now we don't need. Yeah. Now let's come to our so the three I mean Dolphin UFL. These are the most fundamental packages,
For Phoenix, yeah.
and then
But why
PET-C
did they
also we
put
have
like
to.
so Phoenix, so Dolphin X and UFL are part of Phoenix library?
Yes.
Okay,
Yeah.
cool.
Yeah. So now we come to parameters. We choose a length of one and 99 number of elements, and then we created a mesh 1D line mesh using 100 elements, not 100, it's 99 elements or 100 nodes, right? And then we actually defined the endpoint of the domain, which is 0 to length. Now we created the domain, which is dolphin.mesh.createInterval. So here we pass this MPI communication network and then define also pass the argument for the number of elements and also the endpoints. Then it will just construct a mesh with 100 nodes and 19 elements. And I'm just printing that, okay, mesh, how many cells do you have? And it says that it will say that it has 99 cells. Okay. This was not necessary, but yeah, now we come to, we define that,
No,
define
everything is
trial.
necessary. Whatever the extra thing you write, that's the most necessary thing. It's good you wrote all this stuff. Yeah.
Yeah, now we'll define a trial hour. Trial is nothing but the waiting functions. And trial is our solution
Trial
functions,
is
right?
in our nomenclature, whatever the mathematical
It's the
notation we
admissible
use.
function.
So trial is that u, right?
No, trial is S,
So function space,
and
no.
and this is V.
Yeah, I mean, u is belong to S and V belongs to capital V, right? That's what
Yeah,
I've.
yeah, yeah,
Okay.
yeah.
All right, great.
No, and no, this V here is they always used. Okay, I think I'll just note better because it will just create confusions. Here we always define a function space
Oh,
over the
function
entire
space.
domain,
Okay.
and we just have to say, and this is actually a more intuitive way because we always define function space based on the discretization. Because we are working with finite element methods, right? So I mean, we are actually looking to implement it, not from mathematical, not just from a pure maths perspective, right? So that's why, in order to find that, when I mentioned that S of H, that that vector space S of H, right? S of H. So if
Yeah.
S of H, yeah, S of H is something from where we start implementing. So this V is nothing
What do
but
you
S of
mean by
H.
function space? Is that the? Oh, wait. Okay. Now we first you
Yeah,
define
it's
this general function space,
yes,
then you derive trial space and test space from that.
yes,
Okay.
exactly. So what we are doing is we are defining a function space over the domain using Lagrange. I mean, what we have done is that those are Lagrange shape functions, we call them, and
Okay.
we used first order. So you see that?
Can you add a? I want to add a to do, dude, but okay, we'll do it later. We want to see what are the other type of basis
Yeah,
functions
it's
like
yeah, lot.
Lagrange. Euler.
Yeah.
So we
You will
can
have different.
see.
So I'll just call it function space consisting of piecewise linear functions. I think that is best. Then you have u is equal to ufl dot trial function, and it picks up one function from there, and then v is the test function, and that's all from the same function space. And then u of sol is nothing but the solution function that we would like to have later. Then we just call it as dolphin.fem.function v, and we give it the name of displacement. Now we define the source term. So this was before that I was wanting to do it for a general case, but right now not doing. I mean, we'll try to work on it because unless I test it, it's not worthwhile for a tutorial session, right? So I'd only tried it for constant forcing term. In that case, f is equal to dolphin.fem dot
Right.
constant. And then over the entire domain, we have defined the scalar type of with value 6.
Okay.
Even just prescribing domain comma value will also work. Now we come to defining the measure. So d of x is the UFL dot measure dx of the domain. So it defines, like here it works very much in a mathematical sense, right? You clearly see that when we are writing the bilinear form, it is UFL dot inner. So this is nothing but I'll just put it here. So this is what we call as integral from 0 to L, right? And then E, A. This is what we are doing. See, this is what we are what we are what
What
we are
is
doing.
this measure? Okay, so you're literally writing the integral equation here, is it?
Yeah,
Okay,
this dx, right? This is the measure, right? Because it's some element.
correct.
It's like
So if you're dealing with 2D, then you let 2D square. Is that what you write?
it will still be dx. Like dx is a very
No, no, dx is fine. I think if you're dealing with 2D, then I think a will be equal to dx times dx or something like that. Right? If you're dealing with 2D equations, or dx
right,
times
right.
dx times
Yeah.
dy, if I'm not wrong, or
Uh-huh.
maybe, right?
It will it automatically adapts itself based on what the boundary, I mean, what the geometry looks like. So it always gives us the measure of what we call as the, I'll just call it measure itself. It defines the generalized volume element. That's how we should call it.
Great, awesome. Yeah.
Generalized volume element. Not over, we'll just call it for the domain. Even if you don't prescribe it, it will automatically figure out what to do. This is like by default, it knows what to do with X. But we are just prescribing it for the sake of clarity that okay. And then L is the forcing function, right? And this was what we call as this is the one. Interval from 0 to 1, f of x, v of x, dx. Now we define the boundary conditions. So let's first what you call detect the nodes for the left hand side and nodes on the right hand side, right? And then we locate the DOFs, the geometrical DOFs for the left and the right. So this actually gives us node on the left boundary, and which is nothing but just one point in this case, a
Okay.
single node, right? A single
So why
node.
are you writing degrees of freedom? Like, why are you
Yeah,
writing?
this
Why
yeah,
are you
this is
creating a
like
variable with the OF? That's what I'm just wondering.
yeah,
Uh-huh.
this is the
Okay.
these are their functions, right?
Fine, fine, fine. It's okay. It's cool. It's cool. Really smart. Yeah.
This is for the right boundary. Okay, now we'll actually what you call prescribe the boundary conditions. So BCs is dolphin.fem.Dirichlet boundary conditions, and value is pet SC type scalar type of 0 because we are prescribing 0 right on the left hand side. And for which DOFs? The left DOFs, because we are just prescribing u at x is equal to
Yes,
0
yes, yes. Cool, cool,
and
cool.
v is equal to v. Yeah.
And on right side, you have different boundary condition. No, it's
Yeah,
not.
but the
It's
thing
not
is, yeah,
like.
yeah, it is. It should be some. No, no, that we have not put. It's just only on the left hand side.
Oh,
It
yeah,
will
yeah.
put.
I don't know where you'll put the right
And
hand boundary condition. I'm looking for that.
yeah, right now I'm just taking p to be 0.
Ah, okay, great, great,
So
fine, fine, fine.
I'm still
But
learning.
Upar, you defined
Yeah.
P2P6, no? You defined no P2P6,
No, that was
or is it F?
F is equal to
Ah,
F is equal
okay,
to.
okay, fine. That is something nice. I think that is a good assignment to do. Okay,
Yes, yeah.
anyways,
Actually,
yeah.
so we are also learning. So I'll just figure out. Let's figure out how to do for that, and then
Correct, correct. That's
next
true.
time
Right?
we'll
I'm
learn.
just asking. Yeah, it's just something nice to bring up.
Because after this, so what our goal will be, after this, we'll be trying to solve 1D nonlinear problem.
Ah,
Say, say we are having a spring.
non-linear में you can't have bilinear form, no?
No, we cannot have. So we'll just, once we have that form, right, then we can use for other projects as well. It's like,
Okay, so that's
yeah.
great. So my question is, okay, very good that we are solving nonlinear. I want to definitely I will be also involving
Yes.
there.
Hmm,
The question I
hmm.
want to ask is, how much do you think do you deal with any nonlinear equations when it comes to welding processes? You know, if do I make sense?
Uh, yeah, yeah, I understood. I understood. Yeah. Hmm, hmm, hmm.
No, the
I,
original equations we are solving for welding, like welding of the current course, like the
huh.
NPT course, does it involve nonlinear problems? That's what I was wondering. If you can answer that.
Yeah, actually, right now, still these areas have not been taught,
Okay,
have not been discussed so far. So I think we'll see what comes with later, right?
sure,
Yeah.
sure, 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 sure.
So once we have given the Dirichlet boundary condition on the left, now we'll define the
Okay,
problem to be solved, which has to be solved. Yeah. So with this import dolphin.fum.petsy library, see linear algebra. Now what we are doing is we are specifying that we are solving a linear problem, and then we are giving it A, which is the bilinear form. See bilinear form, and L is the linear form on the right hand side. This is the list of Dirichlet boundary conditions, and U is the solution function. It will be created if not provided, and PETC options, like what are options that we want. And let's see here. So PETC options is KSP type is preconditional. I don't understand. I still have to look what is this KSP type.
no worries.
And PC is preconditional type, which is LU decomposition.
Decomposition, yeah,
Yes. And now we can just solve the problem dot solve. And the solution will be found in U solve. Okay,
great.
so then,
Awesome.
yeah,
That's
then we,
cool. It's good.
yeah,
But we haven't discussed how to solve this linear problem and everything in our original.
yeah,
Uh,
actually, there I have, yeah, I have actually, what we did is we actually got the matrix equation to be solved. You just have to put values and invert it and then get the solution.
great, great, great. Well, this is one of the
So,
ways. Yeah, she's very nice, very nice. Yeah.
so now then we can just output the solution file as a VTK file, okay, right? Output dolphin.io.vtk file mpa.com world output, yeah, right, and then we can just start the solution in that VTK file. Yeah, one was that is saved as a for view visualization purpose. Now here we can do is we can use this dolphin.plot.vtk mesh, and the output will be, it will gives us the cells, the type of the cell, and the what do you call, what to speak, and it will also give us these spatial coordinates x. And now I'm just using plot parameters, then plotting it for we just having two subplots, just
That's all
and
okay.
then
That's all okay. It's basic Python plotting. Yeah.
yeah. And here what I did is this I actually solved using Mathematica to get the analytical solution. And then we are actually plotting the exact and numerical solution in this.
Awesome.
You see that there's so much overlap. Yeah.
So can you do something? Can you go to the plot once?
Huh.
Can you write star in the plot of exact or FEM? Because I think you should put uh, you should put exact as star, or if like the solution approximation as star.
I think approximation should be star. Yeah.
Star, right? So can you go to FAM, and in the plot line, can you please
Okay.
write maybe in the R,
This
no?
one,
Can you
right?
put a
Here,
star?
here, here,
Ha, 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 ha.
here will be star, right?
Yeah, yeah.
Something like this, huh?
Yes, exactly.
And all, huh?
Just try it again. Hopefully it works.
Damn.
Yep, yep. There's too
Too
many
close
points. It's fine.
distance.
It's fine. It's too many
I see.
points. Yeah.
I see. Yeah. So yeah, just to compare the results, we just plotted the
And also, when
point-wise
you say it
error.
is red, no, you're
Uh-huh.
plotting red first, and plotting black next. So it is actually on top of it, and like, that's why you can't see red. So if you
Okay, can
can
I change the
just
order? Huh?
move them top, like upar ka niche karo, niche ka upar, then it will be like amazing.
This one, huh?
Yeah, great.
Ah.
Yeah, see, now it's great, right? Yeah, good.
Yeah. Yeah. And then we're just plotting the error also, point-wise
Yeah.
error, and then I don't know why we have UX actually. This is
Also, I
very
have a question here regarding the error plot. Like, I mean, uh, just a small question. Uh, Also, you missed the units, Krishna. Like, is it meters? That one, this one. That's one thing. Like, I want to just um, in
yeah.
the
Actually,
label.
huh, huh, huh.
Just some suggestion. Like, I know we all clear about the units here, but
The thing is, I have not yet prescribed anything yet
anything.
to have it. Yeah.
Okay.
Maybe if we call it say 1 meter,
Yep. 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 Yep.
and then we'll also have to provide the e value also, right?
Yeah.
E is equal to say
How is it auto
12 or
completing like that? E equal to, how
uh-huh.
is it auto complete like this?
Yeah, yeah, I'm using this GitHub Copilot.
This look cool, dude. Wow.
Yeah,
Amazing.
and then
This looks amazing. Man, there's two less of a value. 10. Yeah, that is good.
yeah, and then we'll also have let's also give A is equal to say
Wow, this is
see,
great.
see.
Copilot. I never realized how cool it
Yeah,
could
but
be.
it's
Wow.
not good, man. It just it's good also, but yeah, it also makes us very lazy. So I
It's
just
okay. No, that's how it should be. Good, very good. I'm like, how is this guy getting like even comments? That this? I'm like, what? Yeah, now I see. Okay. So you integrated the Copilot in your VS Code.
yeah, yeah, yeah. You can see it
Amazing.
here. This
Great,
see
great.
it's
And
active. It
Copilot is
says
free
active.
now.
Here you
Copilot
say
is
that
free.
it's not
Yeah,
free.
yeah.
We
Huh?
have to submit our education, this one ID
That's
card
fine.
and
That's fine.
everything.
That's fine. University pays for it, so it's completely fine.
And yeah, so E into A, so we'll have to put here E into A while constructing here. Yeah, here
Coding
E
is easy now, huh?
to
Okay,
A.
good.
Yeah. So now it is complete. And now we can
Yep,
now we'll get some
yep,
realistic answers.
yep,
So and
yep.
we'll also have that right in meters,
So
isn't
the
it?
issue I had with the error plot was you're plotting error on each point. Say that now we'll do it in the next lecture. I mean, next lecture. But
Uh,
the thing I wanted to mention here was um, say that we are changing the number of elements. As we change the number of elements, we have the exact solution. So you are actually
uh,
kind of taking error at each point rather than we can take error out fully, like full discretization was the error. That is more like we can see what is the convergence, what is the order of function, all this stuff,
right,
right? So we
right,
can do
right.
it in the next lecture. But there's
Sure.
something I want to mention to you, like because I never saw. I mean, I have few very little knowledge of the error things. So I was like, you know, make it do that.
Mm-hmm. Sure. So let's run once more.
Yep. Great. Oh, the
Okay,
EA
so
is giving you issues here.
I think the error will be very
Make it
less
one.
now.
Make EA one. Make EA one.
Okay, but okay, why is this exact coming? Okay, exact also have to multiply, right?
Yeah.
I say, why is it giving so less?
True. True.
A into A, right?
Yep.
What?
Oops. This is always there. No, this is always there. It's dangerous. It's not like you just multiply with A. It's not linear. You have to check all the stuff. But it's okay. It's okay.
I see it will, I think it will divide by EA, right? Yeah,
Okay.
yeah, because EA is on the right hand, yeah, so it will divide by EA. Hmm. And then we can also write it as E divided by A, right? This also will work, isn't it?
No,
Yeah. Yeah, no, it's no, this means that it's sequential because it has left to right
no, 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 no,
associativity,
no.
right?
Do E star A in bracket. Why two? I'm not sure.
Yeah.
Never seen this. No,
Yeah,
A goes up
I
actually. A
actually
goes
it
up.
goes from left to right.
No, no, A goes up. No, 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 no. A goes up. I think no. It's very pure mathematics. A goes up if you write like that. Okay, can you? You're doing some zooming. I think you're setting the labels. Can you remove the
Yeah,
labels?
yeah.
Like you're setting the limits of the plot. Remove the limits of the plot.
Okay. I
Set
see, I
limits.
see.
Yeah, yeah.
This
You
one
can
I'll go on.
comment it. Yep,
Here also I'll remove.
yep.
While limit remove, keep
Just
x
for
limit.
small. Yeah,
Yes, yeah,
right.
see.
Works now. Great.
See, the error is 10 power minus 20. Obviously, we this is
See, we
like
have
10
much
power
better
minus.
actually got now. Yeah.
Yeah.
Cool, cool. So we'll stop it here.
Yeah, I'll stop
Stop recording.
recording.
Um,
Yeah.